Assalamualaikum warahmatullah. So in today's lecture, today is on lecture 6. So in today's lecture, we'll start the idea of vector spaces and subspaces. So in this chapter, so this is chapter 3.1, and in this chapter, from chapter 3 and so on, we will see that from the highest level of linear algebra. So instead of looking at individual columns of vector, we would look at the spaces of vectors. Okay. So what does this word spaces mean? When we say vector space, what do we mean by the word space? So it basically means a bunch of vectors or a space of vectors. Okay. So for example, one example of vector space is R2 is a vector space. R2 is a vector space. Alright. So here R2 means all two-dimensional real vectors. So what are the examples of two-dimensional real vectors? Such as, let's say 3, 2, 0, 0, pi, e, etc. Alright. So this R2, as you can guess, this R2 is basically the x y plane. Alright. So to be a vector space, you need to have some characteristics. Okay. So the main characteristic of vector spaces should be if you add two vectors from the vector space, and if you multiply any vector with any scalar, then you should be inside that vector space after that multiplication or addition of two vectors. So means that the result should stay inside that space. Okay. So so do you remember what we mean by vector addition and vector multiplication together? Let's say you have two vectors u and v. So multiplying these two vectors by any scalars means c u, where c is any scalar, and dv, where d is any scalar, and we can add them like this and like this. Alright. So cu plus dv. So this is this means that we have multiplied this vector with a scalar and have added them. So this all together was called, if you could remember, the linear combination. Okay. So this vector space R2 that we are talking about comprises of all the two-dimensional real vectors. Alright. So it should fulfill the condition that the linear combinations of any two vectors in that space should result in that space as well. That means if I take any two vectors from that vector space R2, and if we take any linear combination, then that linear combination should be inside that vector space as well. Only then this should be called as a vector space. Alright, so for example, think about these two vectors. So if we draw our R2, so let's say this is 3 2 and this is pi e. So like if you add these two vectors with, let's say, by scaling 1 at each side, let's say we just add them, so pi plus 3, then e plus 2. So this would also stay inside that vector space, so pi plus 3, e plus 2. Again, if you multiply this 3 2 by any scalar, let's say by -5, so it comes here. Alright, so -5 into 3 2. Sorry. So as you can see that if we take any vector, or if we take any two vectors from R2 and we are taking some linear combination of those two vectors, then the linear combination is staying inside that space, inside that vector space. That's why R2 fulfills the condition of being a vector space. Alright, now think about a scenario where we take out 0 from there. Let's say we remove this 0 0 point, we remove this 0 0 point from any vector space, then can we call it a vector space? The answer is no, because let's say you have taken any vector, this vector and or this vector. Now if we multiply any vector with a scalar 0, with a vector, let's say c equals to 0, then that vector should, or the result should come here. The result should come at this point. Alright, so if I remove this point from the vector space, then as you can see, the linear combination or the scaling does not stay in that vector space after that. So removing 0 0, so 0 0 is a very, or the origin is a very crucial point. Alright, so if you remove 0 0 from any vector space, that does not remain a vector space after that. Okay, so if we summarize, to be a vector space, you need to have two characteristics. The first one is the linear combination of any two vectors from the vector space should stay inside the vector space, or should remain inside the space. And the second one is the origin must be inside the vector space. Alright, so basically, to create a real vector space, you should be able to produce vectors by addition and multiplication. so which follows certain rules like commutative, distributive, so this kind of laws. So commutative law, if I can remember correctly, this is the commutative law, W plus V, and distributive law means C V plus W, CV plus CW. So by following this kind of rules, you can make infinite number of vectors from any. So you can you can produce infinite number of vectors from any vector space. So for example, you can produce infinite number of vectors from this from these three vectors in R2, right? So vector space is a very strong concept in linear algebra. So if I try to give you an example of not a vector space, that would be, let's say this is R2, and we are defining a vector space by the first quadrant. Let's say this one. So suppose we are trying to tell this quadrant a vector space, right? So this quadrant has infinite number of vectors, all right, and all these vectors are positive. So if you take addition of any two vectors, that would stay inside this vector space, so that's fine, all right. But if you multiply any of these vectors by a negative scalar number, let's say by -2 or -5, that multiplication, or by after scaling the vector, that vector comes here at the third quadrant. So this actually violates the rule of a vector space, because this should be inside that the first quadrant to be a vector space. So this is not a vector space. So this is not a vector space, all right. So this violates the first rule. The linear combination of any two vectors from the vector space should stay inside that space. So as I showed, if you take linear combination of any two vectors by scaling it by a negative factor, that linear combination does not stay at the same space. So that is a violation of the characteristic of a vector space. So that is not a vector space, all right. Okay, so tell me a vector space that is inside R2 and closed by multiplication and addition. Okay, so so my question is, tell me a vector space that is inside R2. So the answer would be, if you create, or if you use your imagination, think about any vector. Okay, now think about the positive scalars of the vectors, so that goes to infinity. Okay, now think about the negative scalars of the vectors, so that goes to the opposite direction, to the infinity. All right, now think about this line as a whole. think about this line as a whole. Okay, so if you take any two vectors, let's say you take this vector and this vector, if you take any two vectors and add them, then you will see that you will stay somewhere here. Okay, that means you are staying inside that vector space, so no problem with that. And if you take any negative scalar, or if you multiply any vector from this line, and if you multiply them with a negative scalar number, then you will be staying at the opposite direction. All right, so as you can see that this vector space inside R2 is closed by multiplication and addition inside its own space. All right, so this can be called as a vector space. But as this is a vector space inside another vector space, so this is called a subspace. Okay, so this would be called as a subspace. All right, so this is a subspace. Now, can any line be called as a vector subspace? Suppose we're taking this line. Okay, suppose we're taking this line. Is this a vector subspace? The answer is no, because it is violating the second rule, which is it does not contain the origin. So the origin is not inside that vector space. So why having the origin is important? Because suppose there are many vectors in this vector space. Suppose these are the vectors in the vector space. Now if we add this vector and add this vector, maybe this is the negative scalar of this vector, and if you add them, maybe you are in the origin. All right, but the straight line is not going through the origin. All right, so that is outside of the space, if we call it a space. So this straight line is not a vector space. So to be a vector space, so a line could be a subspace. Line could be a subspace if it goes through the origin. So this condition here is very, very important. All right, this condition right here is very important. So we are talking about two-dimensional spaces. What about three-dimensional space? What about R3? So R3 is basically R3 is a vector space that contains all three-dimensional real vectors, such as let's say any vector 3 2 0. Okay, so R3 is the collection of all the real vectors with three components. Okay, so what about Rn? So Rn is basically all n dimensional real vectors, such as so like any number up to n dimension. Okay, so I hope this point is clear. So as we are talking about R2, so let's stick to R2. So this is R2. Okay, So what are all the possible subspaces? So we just defined subspace here, right? So what are all possible subspaces of R2? What are all possible subspaces of R2? So the first thing is the R2 itself, because every set is a subset of itself, right? So the R2 itself is a subspace. Then secondly can be a line through the origin. So a line through the origin, so a line through the origin is a subspace of R2. And lastly, can you guess the third subspace? So the third subspace is the zero vector, or the origin itself, the zero vector, 0 0. Why? Because if you only think about 0, then so if you only think about 0 0, then if you take any linear combination of this zero vector, that will stay inside that 0 0 vector or on the origin. So the zero vector itself actually fulfills the two conditions to be a vector subspace. Okay, so we can say that zero vector itself is a vector subspace. So can you tell me what are all the possible subspaces of R3? So by the way, the conditions to be a vector subspace is same as the conditions to be vector space as well. All right, so to be a vector space, so to be a vector subspace, the linear combinations of any two vectors should be inside that vector subspace, and the origin should be inside that vector subspace as well. All right, it is same. So can you tell me what are all the possible subspaces of R3? So I think you know the answer, so please do it in the assignment, but I'll give you a hint that the hint is basically the two conditions. That think from the perspective of the two conditions, that what conditions or which subspaces actually fulfills the two conditions to be a vector subspace. Okay, and you'll know the answer. So let's create subspaces out of matrices. Okay, so suppose we have a rectangular matrix as A equals to 1 2 4 and 3 3 1. Okay, so these are the columns with dimension 3. So these are the columns, these are the columns of columns in R3. Okay, so I just cannot put this two column in a subspace and call it a subspace, right, and call it a vector subspace. So what else do you have to call it a subspace? So I must be able to add those things, add those columns, and and the multiplications should be there as well. So that means I should be able to take all linear combinations of the columns to call it as vector subspace. Okay, so so if you summarize, we have to be able to take like all the linear combinations of these two columns, and these linear combinations from their subspace. So that means all the linear combinations that create the subspace is called the column space. Okay, we'll go to column space later, but think about this. Suppose we have, so this is R3, and let's say we define this one as green and this one as red. All right, okay, so the green one is 1 2 4. Let's say this is the 1 2 4. Okay, so this is, let's say, column 1, and the second one is 3 3 1. Let's say this, let's put a negative number here. Let's say this is -3. So suppose this is the column 2. Now I should be able to take all the linear combinations of these two columns. Okay, so all the linear combinations should be going here, going here, going here, going there, going there, going there, going there. So if I take all the linear combinations, you can guess that you will have a plane like structure. You will have a plane like structure, a plane like structure in the R3 space. So this is in fact a plane that goes through the origin. Okay, so this is a subspace because it fulfills all the conditions. So how do I include the origin here? Very simple. We take the scalars as 0. So 0 into column 1 plus 0 into column 2, and by this linear combination we include the origin. Right, now as you can see that this subspace, this spatial subspace, contains all the vectors or all the linear combinations of column 1 and column 2, and it contains the origin as well. So the two conditions of becoming a vector subspace as fulfilled. So this is a vector subspace, and as this subspace is made up of the columns of this matrix, that's why this subspace is called the column space of A, this particular matrix A. Okay, so this is the column space of A. So column space is basically the area or the vector space that is covered by the columns of any matrix A. All right, so this is basically a plane that goes through the origin in R3. Okay, so can you describe the column space of the following matrices? So let's say the first matrix is I equals to, so I2 means 1 0 0 1. So think about all the possible combinations of this two, all the possible combinations that you can make out of this two vectors. You can guess that if we have so this is two-dimensional, okay, and if we take all the linear combinations of these two columns, column 1 and column 2, then we can reach out to any point. We can reach out to any point. You can reach out to any point of R2. Okay, so every vector is a combination of the columns of I. So we can reach any point. Give me one very peculiar example. Let's say for example we are thinking about this minus 2000 and 1500. So can we reach this point? Of course we can, by the help of these two columns. How? By this linear combination, this special linear combination 0 1. So by this special linear combination we can reach at this vector, and like this we can reach out to any point by the potential linear combinations of these vectors, so or of these columns. All right, so the summary is you can reach out to any point in R2 by the columns of the identity matrix. So the identity matrix can fulfill or can cover the whole vector space. So the subspace of this matrix I2 is R2. All right, or the column space of this matrix is R2. Now what is the column space of the vector or the matrix 1 2 2 4? So as you can see, these two columns, okay, can we reach out to any vector, or can we reach out to any point by the help of these two vectors? The answer is, so let's just draw these two vectors. This is 1 2 and this is 2 4. So this is 1 2 and this is 2 4. So you can guess that we cannot reach here. We cannot reach here. Maybe we can reach here, okay, or maybe we can reach like to the infinity throughout this line, but we cannot reach to these two quadrants. So these two quadrants are unreachable, right? So it does not cover the whole. So the answer is simple. By taking all the possible linear combinations, you cannot reach out to every point of R2, or you cannot cover the whole vector space of R2. So you can only cover a line, right? You can only cover a line. So the column space of this should be a line through the origin in R2. Okay, so this is our last example. What about the column space of this particular matrix? So if we had only this, suppose we do not have this part or this column, then this matrix is just another way of representing this matrix, the A matrix. All right, so if we think about only this part, then we can get column space like this. But as we can see that another column is added here. So by the help of these three columns, you can reach out to any point alright. You can reach out to, because this is 1 0, this is 2 0, and maybe this is 3 4, maybe this is 3 4, alright. So you can reach out to any point by taking all the linear combinations with the help of these 3 columns, alright. So this in here, every B is attainable by the help of these 3 columns. So B means this for Ax equals to B. So that means the column space is the whole R2 vector space, alright. So from these 3 examples, you can guess that if you have an n-dimensional matrix and all the columns are independent, then you can reach the whole, or you can fill the whole vector space, and the column space becomes the vector space. Here, in the first example, the first column and the second column are independent of each other, so they can reach out to any point in the R2 vector subspace, and the column space becomes a vector subspace or the vector space. Here these 2 columns are dependent on each other, so 1 2 is just, so 2 4 is just a scalar multiplication of 1 2, so that means they're dependent on each other, and that cannot fill the whole vector subspace or the whole vector space of R2, because this second column does not add anything new with the first column, alright. So this is just a line through the origin, and here we have two independent columns here, suppose this one and this one, or this one and this one. So these 2 columns, so n columns are enough to fill a whole vector space of n dimension. So that's why we could fill the whole vector space of R2. Okay, so in the next discussion class, we will be solving a very important problem on vector subspace and vector spaces and subspaces. So I'll be requesting all of you to attend the next discussion class, inshallah. Okay, so see you in the next class, inshallah. Assalamu alaikum.